Everyone, my name is Aniket Arya and today I will be presenting on the topic perovskite solar cells, the next generation of solar technology. Why solar technology matters now? To begin with, let's understand why solar technology is more important than ever. Global energy demand is projected to increase by nearly 50% by 2050, driven by rapid population growth and industrialization. At the same time, we are facing climate crisis. Scientists warn that we must reduce global carbon emissions by 45% this decade to limit global warming to 1.5 degrees Celsius. Traditional silicon-based solar cells, while widely used, face major limitations. They are expensive to manufacture, their efficiency has almost plateaued, and they are rigid, which limits where they can be installed. This is where perovskite solar cells come into play. They promise high efficiency, low cost, and much more flexibility. What are perovskite solar cells? So what exactly perovskite solar cell means? Perovskite refers to a crystal structure with the general formula ABX3, where A and B are cations and X is an anion. The name comes from Russian mineralogist Lev Perovsky. In solar technology, perovskites are typically organic inorganic halide compounds. For example, methyl ammonium lead iodide, which are excellent at absorbing sunlight and converting it into electricity. The A site is often methyl ammonium Ma+ or formamidinium Fa+. The B site is usually lead Pb2+ or sometimes tin Sn2+. The X site is a halide such as iodine, bromine or chlorine. These materials are cheap, lightweight and can be easily processed, making them highly attractive for next generation solar cells. How perovskite solar cells generate electricity. Now let's look at how perovskite solar cells actually work. Light absorption. The perovskite solar layer absorbs sunlight across a broad spectrum, generating electron-hole pairs very efficiently. Charge separation. These electrons move towards the electron transport layer (ETL), while the holes migrate to the hole transport layer (HTL). Current collection. The separated charges then flow through the transparent front electrode and back electrode, creating a usable electric current. The typical structure of a perovskite solar cell has five layers: a transparent conductive electrode, electron transport layer, perovskite active layer, hole transport layer, and finally a back electrode. Each of these layers is optimized for maximum light absorption and charge extraction, making perovskite cells incredibly efficient. Now, this slide explains about percent of renewable energy source in total literature. It explains geothermal has 3.07%, tidal 3.85%, wave 3.85%, biomass 3.85%, hydropower 2.3%, and wind contribute to 39.23%, and solar technologies contribute to 43.85%. Types of perovskite solar cells architectures. There are three main architectures used in perovskite solar cells: planar heterojunction, mesoporous structure, tandem solar cells. The first one is planar heterojunction, a simple flat layered design where the perovskite is in direct contact with the transport layers. It's easy to manufacture but requires very high quality films. Mesoporous structure uses a porous titanium dioxide scaffold to improve electron collection and charge separation. It's more complex to make but often more efficient. Tandem solar cells. These combine perovskite with silicon in a stacked design. They capture a broader spectrum of sunlight and can exceed the efficiency of either material on its own. Recent breakthroughs advances 2022 to 2025. Between 2022 and 2025, perovskite technology has seen major breakthroughs. In 2022, stability revolution. New encapsulation techniques and molecular additives extended cell lifetimes to over 1000 hours. In 2023, manufacturing scale-up. Roll-to-roll printing was demonstrated for large area production, cutting costs by 40%. In 2024, flexible innovation. Transparent flexible peroxide cells achieved 20% efficiency, opening new possibilities for wearables and building integration. In 2025, efficiency milestone. Peroxide silicon tandem cells surpassed 30% efficiency in commercial prototypes, a major industry achievement. Real-world applications. Peroxide solar cells are now being used or tested in several real-world applications. Building integrated photovoltaics. Transparent PSCs can be built into windows to generate power without compromising aesthetics. Portable electronics. Their lightweight, flexible nature makes them ideal for powering wearables, sensors, and mobile devices. Space technology. Ultra lightweight PSCs are reducing launch costs and powering satellites. Commercial installations. Pilot projects are already using tandem perovskite silicon cells in large solar farms. Challenges and future outlook. Despite their promise, several challenges still need to be overcome. Stability. Peroxides degrade when exposed to moisture, heat, and UV light. Lead toxicity. The most efficient peroxides contain lead, raising environmental concerns, so researchers are exploring tin-based alternatives. Manufacturing scale. Moving from lab-scale production to full-scale manufacturing requires major investment. Looking ahead, future innovations include multi-junction tandem cells with over 35% efficiency, printable solar panels that can be made like newspapers, and smart solar modules with IoT-based self-monitoring. The solar revolution. To conclude, peroxide solar cells represent the most significant advancement in photovoltaic technology since silicon. They combine high efficiency, low cost, and versatility, offering solutions that range from powering skyscrapers to satellites. With continuous improvements, they bring us closer to a sustainable, carbon neutral future where clean energy is affordable and accessible to all. The future of solar is not just coming, it's already here, transforming the way we generate, store, and use energy. References. Here are the main sources I referred to for this presentation, including research papers from NREL, Oxford PV, Science Direct, and key journal articles. These references provide deeper insights into the rapid development and future potential of peroxide solar cells.